Hello everyone, I'm Yunzhe from Peking University, China. Today, I'm here to share our story about designing a dedicated multipath scheduler for LTE network on high-speed railway or HSR. My talk will be divided into 3 parts. Firstly, I will talk about the features of a HSR LTE network and why optimizing performance in such a network is so challenging. Then, I will present our very own design principle of designing multipath schedulers in such a network and introduce our scheduling optimizations. Finally, I will cover the evaluation part, including our real-world experimental setup and our evaluation results. So, let's come to the first part. HSR LTE network has 3 features, namely fluctuating, unpredictable, and heterogeneous, making it very different from wired network or cellular networks under low mobility. So, before we start, let's briefly overview the high-speed railway system in China. In China, traveling by HSR has been very popular because of its high speed, high availability, and convenience. On HSR, the only widely available solution for accessing the internet is cellular network, and currently, LTE is the mostly used network on HSR. So, in the rest of this part, we will show our measurement data collected with long-lived TCP flows on HSR to illustrate the features of the network. Firstly, from the transport layer, we can say that HSR LTE network is fluctuating. On HSR, current throughput and recent throughput could be very different. In about 1/4 of the cases, current throughput fall below half or reach about twice of the recent throughput. Also, the value of RTO based on the measured RTT could be very different from the actual RTT. Therefore, repeated packet timeouts are frequently observed. As a conclusion, HSR LTE network is fluctuating because key performance metrics such as throughput and RTT could change significantly in several RTTs. Secondly, HSR travels along fixed rail tracks, so a common idea would be checking if the performance could be predicted with the location. So, we measure the TCP throughput in multiple travels on the same HSR route to see if the throughput is somehow related with the location or not. However, in most cases, throughput would vary in a large range. And similarly, signal strength also varies over days. Thus, HSR LTE network is very hard to predict in spite of its fixed tracks. Given the fluctuating and unpredictable nature of HSR LTE network, we can hardly provide any means of robust network connection on it. But there is one good thing. Different carriers act differently at the same time. So, leveraging path heterogeneity with multipath transport that uses different carriers at the same time is promising on HSR. However, path heterogeneity can also harm the performance of multipath transport. As we have seen, unfortunately, on HSR, it is common for the LTE networks to be highly heterogeneous. In about 1/4 of the cases, RTT of different carriers differs by at least 1 time. Such a large difference requires us to choose a better path whenever possible. Moreover, we must frequently check the network condition to do this, because the best path changes every several RTTs. So, HSR LTE network is indeed heterogeneous, and such path heterogeneity itself needs to be carefully considered in multipath scheduler design. Okay, so how would those features affect multipath scheduler design? Our answer is they lead to inaccurate performance measurements, which then causes network optimizers to make wrong decisions. Here, we list several previous multipath scheduler designs. By accurately characterizing the network condition, their performance has been better and even more better. It is obvious that by using a more sophisticated network model, we can achieve better performance. However, to correctly understand the network condition, network models need correct input. A more accurate and aggressive model may generate better performance when the network is indeed acting as expected. However, when the measurement results are inaccurate, their performance could be greatly harmed. In fact, transport layer measurements provided by ACK-based feedback only provides information about recent network performance. But to do correct scheduling, we need information about current network performance. The common idea is to assume that the network varies slowly, so we could safely use the recent performance to approximate the current performance. However, this idea does not work on HSR, and in fact, we identify this as a major challenge of designing multipath schedulers or many other network optimizers on HSR. Okay, so given the challenge, what is our solution? We first talk about our idea on the design principle of multipath schedulers. Instead of using a network model to accurately characterize the network, we choose to start from a robust one. To tolerate the inaccuracy of network measurements, then we optimize the network performance whenever an accurate performance indicator is available. More specifically, we use a robust base scheduler to ensure that when we are not sure about the network condition, the performance won't be too bad. And then we detect events that lead to specified optimization actions, or in our words, schedulerlets. A schedulerlet is a scheduler add-on that shapes the behavior of multipath schedulers by manipulating its input and output set instead of modifying its own logic. So, to briefly summarize our idea, we say that we try to understand the network only when it is understandable. Then, let's move on to introduce our event-triggered schedulerlets that performs a real optimization. Due to the time limit, I will quickly go through their high-level ideas and the key insights behind them. The first event we detect is handover failure. We have discussed about the unpredictability of HSR LTE network before, but meanwhile, we also found that handover failures, which may introduce seconds of delay, may be classified and predicted. I omit the details here, but what we need to know now is if a handover did not happen for cell before the train passes a location that could be predicted by us, then the handover would possibly fail. With this knowledge, we design our first schedulerlet, handover failure aware path rejection. It disables the paths that may experience handover failure in the near future to drain the queue and avoid future packet loss due to the handover failure. It not only accelerates the delivery of packets by avoiding losses, but also avoids TCP timeout on the disconnected paths. The second event is when the user session is going to end. With TCP splitting enabled, we can detect this because it acts as a proxy that buffers and forwards user traffic. When the session is going to end, we can try to reduce its tail delay in the cost of some path utilization rate. This is beneficial on HSR because of the large RTD difference on different passes. Following this idea, we design our second schedulerlet, tail-aware path rejection. When we detect a Feng or reset packet of a user session, we activate tail-aware path rejection for it. For all passes, we estimate the one-way delay on it and compare it to the total time needed by using the best path only to complete the session. If the packet will not even arrive before we use the best path to complete the session, we simply discard the path. And also, here we make our delay estimations more conservatively to tolerate inaccurate measurements in the fluctuating network. The third event we detect is that a path was kept idle. In the fluctuating HSR LTE network, we regard this event as a signal for us to bring the performance measurements on such a path up to date. As a response to this, opportunistic redundant traffic injection was proposed by us. It is triggered when a path is not used for some time. Paths are kept idle because they are not preferred by the scheduler due to their performance issues. And this optimization helps the scheduler to discover recently recovered paths. Moreover, the redundancy may also help reduce delivery delay of the copied packets. Here, we note that during the traffic injection, if we detect that the path has at least 8 kilobytes of locally buffered data, the schedulerlets will be instantly disabled to avoid causing queuing on the passes. Then, let's see the last event, repeated retransmission timeouts. If this happens, we know that the error of delay estimation on the corresponding path is very large, and thus we need to perform data recovery with multipath retransmission. Our corresponding schedulerlet is extended reinjection, which is triggered when packets experience alpha repeated timeouts. Instead of reinject packets one by one, like what MPTCP does, extended reinjection reinjects all unactive packets on the corresponding passes. Here, we set alpha to 3 to balance the performance gain and traffic overhead. Also, extended reinjection could only be activated once for each packet sent on each pass. Okay, so with the event trigger schedulerlets, we are now only one step from the complete scheduler design. Let's recall that schedulerlets do not disturb the logic of the base scheduler. So to put them all together, we only need to do, the only thing we need to do is the correct execution order. Here is our composable scheduling framework. It uses multiple pluggable schedulerlets together to form a complete multipath scheduler. I will not dive into this design due to the time limit, because please refer to the paper for details. Instead, to briefly end the design part, we show how our schedulerlets fit a framework. In this work, we use MinRTT scheduler as the base scheduler for its robustness. However, the base scheduler is also pluggable and could be replaced by other schedulers. POLYCORN, as a proxy-based solution that transfers user traffic with multipath connection on HSR, uses this scheduler to enhance its performance. Okay, finally, let's move on to the evaluation part. Here, we introduce the runtime environment of POLYCORN. We deployed POLYCORN on the HSR LTE Gateway, as shown in the figure for our evaluation. It also provides the HSR public Wi-Fi service to passengers. To avoid interfering with passengers' traffic, we acquired exclusive access to 4 interfaces from 2 carriers. We evaluated POLYCORN's performance on Beijing to Shanghai HSR route, the busiest HSR route in China. In 40 trips, we evaluated POLYCORN's performance gain and repeated all our test cases for 50 times. Next, we detail our experimental setup. Due to the fluctuating and heterogeneous nature of HSR LTE network, we must carefully configure our test environment to ensure that our evaluation is fair and representative. In our evaluations, we repeat pairwise tests to achieve this target. We ensure fairness by testing under the same network condition, or in other words, start tests simultaneously. Also, we repeat each test 50 times to collect representative results. Well, still, we note that the variance in the results is comparatively high due to the fluctuating nature of the HSR LTE network. So, let's see our key results. We compare the performance of POLYCORN with state-of-the-art multipath schedulers in single-user file download sessions. We note that except for blast under 256 kilobytes tests, POLYCORN outperforms all multipath schedulers and achieved 57% better performance against its base scheduler, MinRTT. In micro-benchmark tests, we show the gain of individual schedulers of POLYCORN as shown in the right figure. Also, we evaluate the performance of POLYCORN when serving multiple users at the same time to see if POLYCORN is useful for serving applications used by HSR passengers. We test against instant messaging application, the most popular application on HSR. Compared to MPTCP and SP single-pass TCP, where user connections are randomly binding to one LTE interface, POLYCORN reduces message delivery time by 16% and 45% respectively. POLYCORN also helps preserving user-level fairness by scheduling the user traffic in a proportional fair manner. So, as a conclusion, in this work, we study the fluctuating, unpredictable, and heterogeneous nature of HSR LTE network and how they would affect multipath scheduler design in a numerical manner. Based on our findings, we derived our event-driven schedulerlets for optimizing multipath scheduler. Then, we designed and implemented POLYCORN or our own multipath transport solution for HSR LTE network. Finally, we demonstrated POLYCORN's performance under real-world evaluations. Okay, thank you for listening to my talk. Thank our great co-authors and Schaefer that brought this work to life, and I appreciate any incoming questions from you.